Imagine a storage vault so small, 1 billion of them could fit on a single grain of rice, yet it can hold its contents for decades without a single spark of power. This is NAND Flash Memory. It is the silent heart of the digital age, found in everything from the smartphone in your pocket to the massive data centers powering the global cloud. Unlike a traditional hard drive, there are no spinning disks, no moving needles, and no mechanical friction. Instead, it relies on the mastery of quantum mechanics, trapping individual electrons within a microscopic cage. But how do we build a structure so precise that moving a few hundred electrons becomes a permanent record of human history? It begins with the purest material on Earth and a manufacturing process that rivals the complexity of a city, scaled down to the width of a human hair, divided 10,000 times. We are entering a world of nanometers, where light is used as a hammer and chemistry is the architect. This is the journey of how we turn common sand into a digital eternity. The foundation of every memory chip is silicon, the second most abundant element in the Earth's crust. But the sand you find on a beach is far too chaotic for our needs. It must be refined to a purity of 99.9999%, often called 11 nines purity. This raw silicon is melted in a massive crucible at temperatures exceeding 1400 degrees Celsius. A tiny seed crystal is lowered into the molten vat and slowly rotated as it is withdrawn. This is the Czochralski process, a slow-motion dance that creates a single, continuous crystal structure known as an ingot. This silicon log, weighing hundreds of pounds, is then sliced by diamond-tipped saws into wafers, thin, shimmering discs just 775 micrometers thick. Each wafer is polished to a mirror finish, becoming a canvas so smooth that if it were the size of a football field, the largest bump would be smaller than a grain of sugar. This is the blank slate that will eventually hold trillions of bits of data. In the early days of flash memory, we built horizontally, laying out cells like houses in a suburban neighborhood. But eventually, we ran out of space. The solution? We went vertical. This is 3D NAND. The process begins with chemical vapor deposition, or CVD. Inside a vacuum chamber, gases are pumped over the silicon wafer, reacting to leave behind incredibly thin layers of alternating materials, usually silicon dioxide and silicon nitride. We repeat this process over and over, stacking more than 200 layers on top of each other. Think of it as building a 200-story skyscraper where each floor is only a few atoms thick. These layers must be perfectly uniform. Even a slight variation in thickness would cause the memory to fail. At this scale, even a single speck of dust is like a mountain falling on the construction site. This is why the fabrication is done in clean rooms that are thousands of times cleaner than a hospital operating room, where the air is filtered constantly to ensure not a single stray particle disrupts the layering. Once the skyscraper of layers is built, we have to connect them. This requires one of the most difficult feats in modern engineering, high aspect ratio etching. We must drill millions of tiny holes vertically through all 200 layers. These holes are less than 100 nanometers wide, but they are incredibly deep. To visualize this, imagine standing on top of a skyscraper and trying to drill a hole straight down to the basement using a needle, and that hole must be perfectly straight without tilting a fraction of a degree. We use reactive ion etching, blasting the wafer with high-energy plasma. These ions act like microscopic jackhammers, eating away at the material layer by layer. The precision is staggering. If the hole tapers or curves, the memory cells won't line up, and the electrons will leak out. This step is the make-or-break moment for high-capacity SSDs. Once the holes are cleared, they are lined with special materials to create the channel where data will eventually flow. At the heart of every NAND cell is the charge trap layer. This is the cage where we store electrons to represent a 0 or a 1. In traditional flash, we used a floating gate of conductive polysilicon, but in modern 3D NAND, we often use a non-conductive layer, typically silicon nitride. When we want to write data, we apply a high voltage to the word line. This creates an electric field that pulls electrons through an ultra-thin insulating layer via a process called quantum tunneling. The electrons literally teleport through a solid barrier and get stuck in the charge trap. Because the layer is surrounded by high-quality insulators, those electrons have nowhere to go. They are trapped, potentially for 100 years. To read the data, we check if the electrons are there. Their presence creates an electric field that changes how the cell conducts electricity. If the current flows easily, it's a 1. If the trapped electrons block the current, it's a 0. No moving parts, just the presence or absence of a few hundred subatomic particles. With the cells created and the layer stacked, we need to create the roads for the data to travel on. This is the metallization phase. We use a process called dual damascene to etch trenches into the top layers and fill them with copper. These copper lines become the bit lines and word lines that allow the controller to address every single cell in the 3D stack. It is a three-dimensional grid of staggering complexity. Every single cell must be reachable. If you could zoom in and walk through this structure, it would look like a futuristic metropolis with glowing copper highways stretching for miles. To ensure the signals move at lightning speed, we use low-K dielectrics, special insulating materials that prevent electrical interference between the wires. At this scale, wires are so close together that they can actually talk to each other through electromagnetic induction. Engineering these barriers is what allows modern SSDs to reach speeds of over 10 gigabytes per second. A NAND flash chip on its own is just a collection of vaults. To make it useful, it needs a brain, the flash controller. This is a separate, highly specialized processor that manages where data is stored. Because NAND cells can only be written to a finite number of times before the insulating layers break down, the controller performs wear leveling. It moves data around constantly, ensuring that no single cell wears out faster than the others. It also performs error correction. At the nanometer scale, cosmic rays or heat can occasionally knock an electron out of its trap. The controller uses complex math, Reed-Solomon or LDPC codes, to detect and fix these errors in real time. The controller is what makes the SSD feel fast and reliable. It manages the flash translation layer, which acts like a librarian, keeping track of trillions of bits across multiple chips. Without the controller, the trapped electrons would be nothing but digital noise. Before any NAND chip leaves the factory, it must prove it can survive the real world. We subject these chips to the torture test. They are placed in ovens and heated to over 100 degrees Celsius, then instantly chilled to -40. This thermal cycling tests the integrity of the layers and the copper connections. We also perform data retention tests, where we write data and then subject the chip to high heat to simulate years of aging in just a few days. If a single bit flips or a connection cracks, the entire chip is discarded. We use automated optical inspection and scanning electron microscopes to look for defects that are invisible to the human eye. Only the prime silicon survives. These are the chips that end up in your high-end gaming rigs and enterprise servers. The chips that fail the highest standards might be used in lower speed applications like USB drives or toys. This rigorous screening ensures that when you save your family photos, those electrons stay trapped exactly where they belong. The result of this journey is the M.2 SSD, a slate of block circuit board no larger than a stick of gum, yet capable of holding 8 terabytes of data. That is roughly 2 million songs, or 4 million high-resolution photos. Behind that simple exterior lies the work of thousands of engineers and the most precise manufacturing machines ever built by man. We have learned to manipulate matter at the atomic level, stacking layers of light and shadow to create a permanent home for the digital ghosts of our lives. NAND flash memory is more than just storage. It is a testament to the mastery of the electron. From the refinement of raw quartz to the quantum tunneling of subatomic particles, we have built a way to trap information for eternity. The next time you save a file, remember, you are commanding a microscopic city to capture a lightning bolt and keep it still, forever. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.